So even though my project is publicly accessible, there are just too many dependencies that you need for it to work, so I'm not going to bother with that. I'm just going to do video demo. So what my project is a molecular dynamic simulation. I'll explain what that is in a second, but I'll run it right here using a bash script, and it will prompt for the number of molecules. I'll just say 200, and the upper bound, which I'll explain later, and the target temperature, which I'll say will be 500. So it's going to ask for a type of molecule. I'm doing noble gases because those are the easiest type of molecule to model, because they're monoatomic and they're relatively unreactive, so it's very easy to predict the forces, since there's only one type of force, which is van der Waals forces. So I'll say one type helium molecules, and another type will be xenon molecules. So these are the time steps. For each time step, it's calculating a bunch of things like the position, the velocity, the acceleration, and it has to do a lot of these calculations, as you can see, so it takes a little bit to finish all of that. And when it's finished, it will create a trajectory file, and then it will also load it into VMD, which is the tool I'm using. It's pretty much a 3D visualization software for these types of trajectory files. So over here, you can see that the white molecules, or the helium molecules, they move a lot faster than the xenon molecules, which have a much higher mass. And this is the periodic box. Pretty much what happens is that this is meant to resemble like one small part of a very large system, which is why you see molecules kind of like phasing out and back into the box. That's done on purpose, because that, for one, makes the calculations much easier, and that also helps to reflect what an actual very large simulation would be like. So that's how the simulation does it very efficiently. And you can also do this with a variety of molecules. I'll just run it again, this time with 100 molecules. I'll say the upper bound is 25, and I'll do a much lower temperature for this time. So I'll do, let's say, 25 helium molecules, 25 neon molecules, do like 10 radon molecules, 20 xenon molecules, and I guess 20 krypton molecules. So it's going to run the calculations again, and once it's finished, it's going to load them in VMD. And now you can see, was a bit hard to see because the boundaries are smaller, but there's also less molecules. So you can see there's different colors, those represent the different elements, and you can see that they're moving a lot slower. Helium's still moving a bit fast because it's a light element, but you can see how the krypton, argon, radon, they're hardly moving at all, and that's to be expected at a temperature this low. And that's pretty much what I have.